The asteroid that could end life on Earth. Imagine you are standing outside, late at night, somewhere far from the city. The sky above you is perfectly clear, a vast black canvas scattered with thousands of points of light. The Milky Way stretches across the heavens in a pale, ghostly arc. It is one of those rare moments when you feel genuinely small, genuinely aware of how enormous the universe is and how fragile you are within it. You tilt your head back and breathe in the cool night air, and for a brief, beautiful moment, you feel at peace. Then you see it. It begins as nothing more than a faint smudge among the stars, barely distinguishable from the background glow, but over the course of a few minutes, it moves, slowly at first, then faster. A dim, steady point of light that does not blink, does not flicker, does not behave like any star you have ever seen. Your eyes follow it across the sky, and somewhere deep in the ancient animal part of your brain, a signal fires. Something is wrong, something is coming, and it is aimed directly at us. This is not a science fiction story. This is not a Hollywood screenplay. What I am about to tell you is based on real physics, real mathematics, real geological and astronomical science. The threat we are going to discuss tonight exists. It has existed since long before the first human being ever drew breath on this planet. And if the universe runs its course without our intervention, it will exist long after the last human being has gone. Tonight, we are going to talk about asteroid impact. We are going to talk about what it actually means, not the sanitized popcorn movie version, but the raw, physical, geological, biological reality of what happens when a rock the size of a mountain, or a small city, or a nation strikes the Earth at 70,000 kilometers per hour. We are going to talk about the asteroids we already know exist, the ones we are watching right now with our telescopes and our radar systems and our very anxious eyes. And we are going to talk about what the universe has already done to this planet and what it could do again. Because, make no mistake, this has happened before. It will happen again. The only question is when. Part 1. The nature of the threat. Before we go any further, I need you to understand something about the solar system you live in. Most of us carry around a mental image of the solar system that we absorbed in childhood. The sun at the center, 8 planets marching outward in orderly, well-behaved ellipses, everything clean and stable and predictable. A kind of cosmic clockwork ticking away in silence. That image is a lie. The reality of the solar system is far messier, far more violent, and far more dangerous than any classroom poster ever suggested. Between Mars and Jupiter, there is a region of space called the asteroid belt, a vast, sprawling collection of rocky and metallic objects ranging in size from tiny grains of dust to Ceres, a dwarf planet nearly 1,000 kilometers across. There are estimated to be more than 1 million asteroids in the main belt alone that are larger than 1 kilometer in diameter. More than 1 million. And those are just the ones we have found. But the main belt is not the only place where asteroids live. Through the complex gravitational choreography of Jupiter, Saturn, and the other giant planets, asteroids are regularly nudged out of their stable orbits and sent on new trajectories. Some of these trajectories cross the orbit of Mars. Some cross the orbit of Earth. These are the ones we call near-Earth asteroids, or NEAs. And as of today, we have identified more than 33,000 of them. 33,000 rocks in space, many of them crossing the path of our planet, on orbits that bring them close, sometimes very close, to the place we call home. Among these, there is a special category that should make you pause every time you look up at the night sky. They are called potentially hazardous asteroids, or PHAs. These are the ones that come close enough to Earth, within about 7.5 million kilometers, and are large enough, greater than about 140 meters in diameter, that a future impact cannot be entirely ruled out. As of today, we have identified more than 2,300 potentially hazardous asteroids, 2,300 known rocks in space, each one a potential civilization-ending event. Each one following its own precise orbital path, governed by the cold, indifferent mathematics of gravity, with no regard whatsoever for the pale blue dot sitting in its path. Now, I want to be careful here. I want to be scientifically honest with you, because that is what you deserve. The vast majority of near-Earth asteroids are not on a collision course with Earth. Most of them will pass by harmlessly, missing us by millions of kilometers. But quite low is not zero. And when we are talking about an event that could kill millions of people, or billions, or potentially every complex living thing on the surface of this planet, quite low becomes a number you cannot ignore. Let me give you a sense of scale. The rock that killed the dinosaurs, the impactor responsible for the Cretaceous-Paleogene extinction event 66 million years ago, is estimated to have been roughly 10 to 15 kilometers in diameter. It struck what is now the Yucatan Peninsula in Mexico at a speed of approximately 20 kilometers per second. The energy released by that impact was equivalent to roughly 1 billion nuclear bombs detonating simultaneously. Within hours, the impact site was engulfed in a firestorm stretching thousands of kilometers. Within days, a massive cloud of dust, ash, and vaporized rock was spreading across the globe, blocking sunlight. Within weeks, global temperatures had begun to plummet. Within months, photosynthesis had largely collapsed across the planet. Within years, the food chain had unraveled so catastrophically that approximately 75% of all species on Earth, including all non-avian dinosaurs, had been wiped out. The ocean boiled for hundreds of kilometers around the impact site. Rocks were flung into suborbital trajectories and rained back down across the planet, heating the atmosphere as they re-entered. Earthquakes of a magnitude never experienced in human history shook the entire planet simultaneously. Tsunamis, hundreds of meters tall, swept across ocean basins and inundated coastlines thousands of kilometers from the impact point. This actually happened. This was not a thought experiment. This was Tuesday, 66 million years ago, on planet Earth. And the universe has not changed since then. The asteroids are still out there. Gravity still works the same way. The physics of kinetic energy has not been repealed. The only thing that is different now is that we are here, and we know about the threat. Part 2. The ones we are watching. Let me introduce you to some specific asteroids because I think it is important to understand that this threat is not abstract. These are real objects with real names, real measured orbits, and real calculated probabilities of impact. Let us start with Bennu. Bennu is an asteroid approximately 500 meters in diameter, about the height of the Empire State Building from base to antenna. It is dark, roughly spherical, and tumbles slowly through space on an orbit that brings it close to Earth roughly every 6 years. NASA's OSIRIS-REx spacecraft actually visited Bennu, orbited it for more than 2 years, and collected a sample of its surface material, which was returned to Earth in 2023. We know a great deal about Bennu, and what we know is not entirely comforting. Current calculations give Bennu a roughly 1 in 1,700 chance of striking Earth before the year 2300. The most likely impact window is in September 2182, specifically September 24th, 2182, when Bennu will pass exceptionally close to Earth. Whether it actually strikes us depends on a phenomenon called the Yarkovsky effect, which is the subtle but cumulative force exerted on an asteroid by the way it absorbs sunlight and radiates heat. Because Bennu is a real three-dimensional thermally active object rotating in space, it does not follow a perfectly calculated Newtonian orbit. Tiny thermal forces push it, millimeter by millimeter, year by year, slowly adjusting its path in ways that are difficult to predict precisely over very long timescales. If Bennu were to impact Earth, the energy released would be equivalent to roughly 1,200 megatons of TNT, approximately 80,000 Hiroshima bombs. It would not be a global extinction event, but it would be catastrophic. If it struck a city, that city would cease to exist instantly, and the region surrounding it would be devastated for hundreds of kilometers in every direction. If it struck the ocean, the resulting tsunami would be enormous, potentially inundating coastlines across entire ocean basins. 1 in 1,700. In terms of daily life, that sounds small. You probably would not worry about odds like those for most things. But think about it this way. If there were a 1 in 1,700 chance that the city you live in would be completely destroyed before the end of the 22nd century, would you find that comforting? Would that feel like nothing? And Bennu is not alone. There is Apophis. For a few years after its discovery in 2004, Apophis was considered one of the most dangerous known asteroids in the solar system. Early orbital calculations gave it a disturbingly high probability of striking Earth on April 13, 2029. For a brief period, the odds reached as high as 1 in 37. The world's media paid attention. Scientists paid a great deal of attention. And then, as more observations were collected and the orbital calculations refined, the 2029 impact was ruled out. Apophis will pass Earth in 2029, but it will pass very close. Closer than many of our own satellites. Close enough that it will be visible to the naked eye as it streaks across the sky. A 340-meter rock moving at roughly 30 kilometers per second, passing within 31,000 kilometers of Earth's surface. That is closer than the ring of geostationary satellites that carry our television broadcasts and our weather data. And then there is a category of asteroids that is, in many ways, more frightening than Apophis or Bennu. These are the ones we have not found yet. Part 3. The ones we do not know about. Here is a number I want you to sit with for a moment. We estimate that there are approximately 25,000 near-Earth asteroids larger than 140 meters in diameter. As of now, we have found and cataloged roughly 10,000 of them, which means there are approximately 15,000 large asteroids crossing Earth's orbit that we have not yet found. 15,000 potentially hazardous rocks in space, some of which may be on trajectories that bring them into direct contact with our planet, and we have no idea where they are. This is not a failure of science. This is the reality of the search problem. Space is enormous, asteroids are dark, and even with our most powerful telescopes, detecting a dark rock against the black background of space is extraordinarily difficult. We are getting better at it, dramatically better, with new survey programs scanning larger portions of the sky more frequently than ever before. But there is a particular category of asteroid that will always be harder to find than the rest. These are the asteroids that approach Earth from the direction of the Sun, because our telescopes can only operate when looking away from the Sun. Otherwise, the sunlight overwhelms any signal from a distant rock. There is a blind spot in our sky. An asteroid approaching from the day side could, in principle, appear with almost no warning. Days, hours, perhaps none at all. This is exactly what happened on February 15, 2013, over Chelyabinsk, Russia. A 20-meter rock entered Earth's atmosphere at approximately 19 kilometers per second and exploded at an altitude of about 30 kilometers above the city. The explosion, a so-called airburst, released the energy equivalent of roughly 500 kilotons of TNT. The shockwave shattered windows across an area of 7,000 square kilometers. More than 1,500 people were injured by flying glass. The event was captured on dozens of dashboard cameras, surveillance systems, and smartphones, a stunning visual record of just how suddenly and dramatically an asteroid impact can announce itself. Nobody saw it coming. Not a single telescope on Earth had detected it before it hit. It came from the direction of the Sun, and it arrived without warning. And Chelyabinsk was 20 meters across, a rounding error in asteroid terms, a pebble compared to Bennu, a grain of sand compared to the rock that killed the dinosaurs. Imagine the same scenario, but the rock is 140 meters across, or 500 meters, or 2 kilometers. Part 4. The physics of annihilation. I want to walk you through what actually happens when an asteroid strikes Earth. Not the movie version, not the dramatic heroics and the stirring music and the miraculous last-second escape. The real version, the physical, geological, atmospheric, biological reality of kinetic impact on a planetary surface. Let us use a specific example. Let us say an asteroid 1 kilometer in diameter strikes Earth. 1 kilometer, that is about the length of 10 American football fields laid end to end. It is not the largest asteroid that could hit us. It is not the dinosaur killer. It is a medium-sized threat. And here is what happens. The asteroid enters Earth's atmosphere at somewhere between 11 and 72 kilometers per second. Let us use 20 kilometers per second. At this speed, friction with the atmosphere begins to heat the rock's surface to thousands of degrees almost immediately. But a 1 kilometer rock has so much mass, So much momentum that the atmosphere barely slows it at all. For all practical purposes, it passes through the atmosphere in about 2 seconds. Nobody on the surface sees it coming. Not really. You might see a streak of light brighter than the sun. You might feel a pressure wave, and then it hits. The impact itself is almost impossible to conceptualize. When a 1-kilometer rock strikes the ground at 20 kilometers per second, the kinetic energy released is on the order of 47,000 megatons of TNT. That is more than 3 million Hiroshima bombs. In the first fraction of a second, the rock and a substantial volume of the ground beneath it are both vaporized. Not melted, vaporized. Converted directly from solid matter to superheated plasma and gas, expanding outward at supersonic speeds. A crater forms in a matter of seconds, roughly 10 to 15 kilometers across. But the damage does not stop at the crater's edge. Far from it. The pressure wave from the impact propagates outward at the speed of sound and beyond. Within a radius of several hundred kilometers, the overpressure from the shockwave is sufficient to collapse buildings, rupture eardrums, and knock people off their feet. Winds driven by the pressure wave reach speeds of hundreds of kilometers per hour. Within a radius of roughly 100 kilometers from the impact site, the combination of overpressure and thermal radiation is likely lethal to most unprotected humans. The fireball itself rises above the impact site, reaching temperatures of tens of thousands of degrees. This fireball radiates thermal energy outward in all directions. If you are within a few hundred kilometers of the impact site, the thermal pulse ignites everything that can burn. Forests, buildings, you. And then comes the seismic event, an earthquake equivalent to approximately magnitude 8 on the Richter scale. The ground ripples outward from the crater like the surface of a lake struck by a stone. If the asteroid strikes an ocean, and remember, oceans cover roughly 70% of Earth's surface, a mega tsunami is generated. For a 1-kilometer impactor striking the deep ocean, the initial wave height near the impact site could reach hundreds of meters. Coastal cities across entire ocean basins face walls of water arriving with almost no warning. But even all of this, the fireball, the shock wave, the tsunami, the earthquake, is not the most dangerous part. The most dangerous part is what happens to the atmosphere. When the asteroid hits, a vast quantity of material is ejected upward into the atmosphere and beyond. Fine particulate matter, dust, ash, vaporized rock, enters the stratosphere and spreads globally within weeks. This material blocks sunlight, and when sunlight is blocked, the consequences cascade through the entire biosphere with terrifying speed. Without sunlight, photosynthesis slows. Without photosynthesis, plant growth collapses. Without plant growth, the food web begins to unravel from the bottom. Herbivores starve. Carnivores follow. For a 1-kilometer impactor, the atmospheric effects are severe, but not necessarily civilization-ending on a global scale. For an impactor of 5 or 10 kilometers, like the dinosaur killer, the effects are catastrophic. The so-called impact winter that follows a large strike could last years or even decades, during which global temperatures drop sharply, agricultural systems fail worldwide, and starvation becomes the dominant cause of human death. This is not science fiction. This is what the geological record tells us happened 66 million years ago. The evidence is everywhere, if you know where to look. There is a thin layer of iridium, an element rare on Earth but common in asteroids, found at the same geological stratum worldwide, the so-called KPG boundary. There is shocked quartz, mineral crystals deformed by the extreme pressures of impact, found across the globe. There is a layer of spherules. Tiny glass beads form from rock vaporized by the impact and then resolidified as it fell back from the stratosphere. All of it, everywhere on Earth, at the same geological moment. The universe left its mark. It always does. Part 5. The Geological Record of Horror. You might think that a world-altering asteroid impact is a once-in-a-billion-year event, an unimaginable fluke. Something so rare that worrying about it is like worrying about being struck by lightning while simultaneously being eaten by a shark. The geological record disagrees with you. Earth currently has approximately 190 confirmed impact craters. 190 times in the history of this planet, a rock from space struck with enough force to leave a permanent scar in the ground. And those are just the ones we can still see. Most of the craters from the early history of the planet have been erased by erosion, tectonic activity, and the slow geological churn of a living planet. There is the Vredefort crater in South Africa, approximately 300 kilometers across, formed about 2 billion years ago. The impactor that created it was estimated to be roughly 10 to 15 kilometers in diameter. Sound familiar? That is approximately the same size as the dinosaur killer. 2 billion years ago, something roughly equivalent to the KPG impactor struck what is now South Africa. There is the Sudbury Basin in Ontario, Canada. A crater originally estimated at more than 250 kilometers across, formed about 1.8 billion years ago. The Sudbury impact was so energetic that it melted a vast volume of the Earth's crust, forming the enormous nickel and copper deposits that have made Sudbury one of the most economically significant mining regions on Earth. These are not ancient myths. These are real, measurable, scientifically confirmed events. Large rocks have struck this planet many times in its history, with consequences ranging from regional devastation to global catastrophe. And the asteroids that caused them did not announce themselves in advance. They did not ask for permission. They followed the mathematics of gravity, indifferent to whatever was living on the surface below, and they struck. What this means, practically speaking, is that impact events happen on a regular geological schedule. The bigger the impactor, the rarer the event. But even the rarest events happen eventually. An impact capable of regional devastation, something in the range of a few hundred meters, occurs statistically once every few thousand to tens of thousands of years. An impact capable of global climatic disruption, something in the kilometer range, occurs roughly once every few 100,000 to million years. A true civilization ender, the dinosaur killer scale, occurs roughly once every 100 million years. Once every 100 million years sounds like a long time, and it is. But let me ask you something. What is 100 million years divided by the approximately 300,000-year history of anatomically modern Homo sapiens? About 1/3 of 1%. We have been here for 1/3 of 1% of the time between extinction-level impacts. The clock does not reset for us. The universe does not care how long we have been here. The countdown was already running when the first human being looked up at the night sky and saw a smudge of light moving slowly among the stars. Part 6. The day it happens. Let me take you somewhere specific. Let me take you to the day it happens. Not a hypothetical day. A real physical reconstruction of what a large impact event actually looks like, from the first second to the last. It is an ordinary morning. People are commuting to work, making coffee, dropping children off at school. The asteroid is not in any telescope data because it came from the direction of the sun. At a height of roughly 80 kilometers above the surface, the asteroid enters the atmosphere, but this is almost meaningless. The atmosphere at 80 kilometers altitude is so thin that it offers almost no resistance to something with this much momentum. At 30 kilometers altitude, the rock is a fireball. The surface temperature has exceeded 10,000 degrees. A bright trail of superheated gas, ionized air, and vaporized rock streams behind it. At 20 kilometers altitude, the sonic boom reaches the ground before the impact does, a sound like God clearing his throat. People who hear it and look up will have approximately 2 seconds to see what is coming. At the surface, the impact is not a sound or a sight or a feeling. It is an event so instantaneous, so locally catastrophic, that the distinction between the rock and the ground ceases to have meaning. They both become something else. A plasma, an explosion, an expanding sphere of devastation. In the first milliseconds, the impactor and several cubic kilometers of ground are vaporized. The transient crater reaches its maximum depth within seconds. In the first seconds, a massive ejecta curtain rises into the sky. Rock, dust, and molten material are thrown upward and outward. Some of this material leaves Earth's atmosphere entirely and enters orbit. Some of it falls back as a rain of molten rock droplets across thousands of kilometers, igniting fires far from the impact site. In the first minutes, the shockwave expands outward at supersonic speed. Within this shockwave front, the air pressure momentarily exceeds the structural limits of virtually anything built by human beings. Buildings do not collapse, they disintegrate. If this is a city, the city ceases to exist in the time it takes you to draw a breath. In the first hours, the thermal plume rises tens of kilometers into the stratosphere. Tremendous quantities of fine dust begin spreading outward at the level of the jet stream. In the first days, the ejecta in the stratosphere begins to distribute globally. The sky takes on a reddish, hazy character. Sunsets are spectacular and apocalyptic simultaneously. In the first weeks, global average temperatures begin to fall. People far from the impact notice that the sky looks different, that it is slightly colder than it should be, that sunlight seems dim. In the first months, agricultural systems show stress. The northern growing regions experience frost events outside the normal season. Harvests fail or are severely reduced. In the first years, if the impactor was large enough, the climate disruption deepens. Global food systems begin to fracture. Prices rise. Distribution systems are strained. Political stability in vulnerable regions erodes. This is not a worst-case scenario. This is what the physics says would happen. Every single step in this chain of events is physically inevitable given the initial conditions. Part 7. What we are doing about it. Here is where the story changes. For the first time in the 4.5 billion year history of this planet, there is a species living on the surface that knows about the threat, that understands the physics, that has the capacity, perhaps, to do something about it. We are the first species in Earth's history that could, conceivably, prevent an extinction-level impact. And whether or not we will actually succeed is one of the most important open questions in human civilization. The first step is detection. You cannot deflect an asteroid you do not know about. This is why the survey programs matter so much. Programs like NASA's Center for Near-Earth Object Studies and the Catalina Sky Survey, which are collectively scanning the sky and building a catalog of near-Earth asteroids. Every year, the catalog grows. Every newly discovered asteroid that gets characterized and ruled out as non-threatening is one less unknown, one less potential catastrophe lurking in the dark. But detection is only the beginning. Once you find an asteroid on a collision course, you need to move it. And moving an asteroid is one of the hardest engineering problems the human species has ever faced. There are several proposed methods for deflecting an asteroid. The most straightforward conceptually is the kinetic impactor. You build a spacecraft, aim it at the asteroid, and crash it into the asteroid at very high speed. The momentum transfer from the spacecraft changes the asteroid's velocity very slightly. If you do this early enough, years or decades before the predicted impact, that tiny change in velocity accumulated over time translates into a change in the asteroid's orbit large enough to miss Earth entirely. This is not theoretical. We have actually done it. On September 26, 2022, NASA's DART spacecraft, the Double Asteroid Redirection Test, deliberately crashed into a small asteroid called Dimorphos. The impact changed Dimorphos's orbital period by approximately 33 minutes, significantly more than the predicted minimum of 73 seconds. The test was a striking success. We can move asteroids. We have proved it. But here is where the heroic narrative starts to run into uncomfortable physics. The DART test worked on Dimorphos, which is about 160 meters across. The asteroids that pose the greatest threat are often much larger. Bennu is 500 meters across. Apophis is 340 meters across. A dinosaur killer would be 5,000 meters or more. The amount of momentum you need to change the trajectory of a larger asteroid scales with the mass, and mass scales with the cube of the diameter. An asteroid twice as wide has 8 times the mass. An asteroid 10 times as wide has 1,000 times the mass. To deflect a 10-kilometer asteroid using a kinetic impactor, you would need either a spacecraft 1,000 times more massive than DART, or you would need to hit it 1,000 times, and you would need years of warning. Ideally, decades. Here is the critical constraint. Deflection time is everything. If you discover an asteroid on a collision course tomorrow, and the impact is 6 months away, it is almost certainly too late to deflect it. But if you find that same asteroid 20 years before impact, the problem becomes tractable. A small velocity change applied early produces a large positional change by the time the asteroid reaches Earth's orbit. This is why the survey programs are so important, not just as scientific exercises, but as the first line of defense in a planetary protection system. Every telescope hour spent searching for near-Earth asteroids is an investment in warning time, and the universe, in its indifference, is not impressed by our timelines. Part 8. The terrifying arithmetic of ignorance. Let me bring this back to the present moment, to tonight, right now as you watch this video. There are approximately 15,000 near-Earth asteroids larger than 140 meters that we have not yet found. Some of them are almost certainly on orbits that bring them close to Earth. A small fraction of those, a very small fraction but not zero, may be on trajectories that will bring them into direct contact with Earth's surface within the next century or two. We do not know which ones. We do not know where they are tonight. We do not know when or if one of them will step out of the darkness and announce itself by lighting up the sky. This is the uncomfortable fact at the center of the asteroid impact threat. The danger is not from the asteroids we know about. The danger is from the ones we do not. The Chelyabinsk rock arrived without warning and was 20 meters across. The devastation was measured in broken windows and injured people. Now scale that up. A 140-meter rock arriving from the direction of the sun with days of warning. A 500-meter rock arriving with a week's notice. A 2-kilometer rock that nobody found because it was dark and it came from the wrong direction. What do you do? What does anyone do? The honest answer is not much. With days of warning, the options are essentially limited to evacuation of the impact zone, if you know where the impact will occur precisely enough to know which zone to evacuate. With a week, you might get some planning done. But deflection? No. No spacecraft can be built, launched, and navigated to an intercept trajectory in days or weeks. This is why the survey programs need more resources. This is why the Vera Rubin Observatory matters. This is why missions like DART are not optional extras in the scientific budget. They are investments in the survival of civilization. And here is the thing about asteroid impact risk that separates it from most other existential threats. It is one of the few threats that is, in principle, completely preventable. An asteroid is governed by physics. It follows the laws of gravity with perfect, predictable precision. If we know it is coming with enough lead time, we can move it. We can solve this problem completely, permanently, with the technology we already have or can develop with modest investment. The only thing standing between us and a solved problem is time and awareness and the political will to take it seriously. Part 9. The Weight of Deep Time. I want to take a step back from the technical details for a moment and ask you to feel something. 66 million years ago, the most complex ecosystem the Earth had ever produced was alive. The age of dinosaurs, 165 million years of evolution, adaptation, ecological development, had produced a biosphere of extraordinary richness and complexity. Giant herbivores that stripped vegetation across entire landscapes, vast predators at the top of intricate food chains, flying creatures that ruled the skies, marine reptiles that dominated the oceans, an entire world in full operation, completely unaware of what was coming. And then a rock arrived from space. And all of it, every species, every ecosystem, every thread of that 165 million year tapestry came apart. Not slowly, not gradually, suddenly. Within a human lifetime after the impact, the world was essentially unrecognizable. The food web had been severed at its base. The dominant organisms on land were gone. The oceans were disrupted. The skies were full of dust. From that devastation over tens of millions of years, a new world emerged, a world of mammals and birds, a world that eventually produced something unprecedented, a thinking species, a species that could look up at the night sky and understand with mathematical precision exactly what had destroyed the previous world. A species that could calculate orbital trajectories and design spacecraft and conceive of genuinely preventing the thing that killed the dinosaurs. That species is us, and we are at, arguably, the most important moment in this entire story. The moment where a species on Earth first becomes capable of interrupting the cycle, of breaking the pattern of blind impact events that has shaped the history of this planet for 4 billion years, of consciously, deliberately, using the intelligence that evolution produced to protect the living world from the indifference of the cosmos. It is a breathtaking moment to be alive in. And it is a terrifying one, because we are also at the moment where we might fail. where budget constraints and political priorities and the simple human tendency to not worry about low probability events might lead us to underinvest in the survey programs, to delay the development of deflection technologies, to assume that because nothing has happened in recorded human history, nothing will happen in the near future. That assumption has a name. It is called the gambler's fallacy. The universe does not remember that it has not hit us recently. The clock does not reset. Every year that passes without a large impact is not a year of safety. It is a year closer to the next large impact. Part 10. The most important thing you have never worried about here is a question I want you to take with you after this video ends. Why do we spend trillions of dollars every year on military defense, building weapons systems designed to protect us from other human beings, from threats that we deliberately create for each other, and comparatively almost nothing on planetary defense, on protection from the one threat that has actually caused mass extinctions on this planet, the one threat that is indifferent to politics, that cannot be negotiated with, that cannot be deterred, and that, if it arrives, will not spare anyone regardless of what nation they belong to or what ideology they hold. The total annual budget of NASA's Planetary Defense Coordination Office is approximately $150 million. $150 million. The United States spends more than that every 12 hours on military operations. The world spends that amount on defense roughly every 90 seconds. I am not making a political argument. I am making a mathematical one. The expected cost of an undetected, undeflected large asteroid impact, measured in terms of lives lost, infrastructure destroyed, economic output eliminated, is enormous. Truly enormous. Trillions upon trillions of dollars, potentially the entire accumulated wealth and infrastructure of human civilization, and the cost of preventing it, of completing the survey catalog, of developing and testing deflection technologies, of building an early warning system worthy of the name, is, by comparison, trivially small. This is not a difficult equation. It is one of the clearest cost-benefit calculations in the history of public policy. And yet we continue to underfund it, because the threat does not make headlines unless there is a close approach to worry about, because the timescales involved do not align with electoral cycles, and because human psychology is not well designed for assessing very low probability, very high consequence events. We are, in this respect, exactly like the dinosaurs, not because we lack intelligence, not because we lack the capability, but because having intelligence and capability is not the same as using them. Part 11. The philosophical weight of the cosmos. Let me bring this to a close. Somewhere out there, right now, is a rock. It might be small, a few meters across, a few tens of meters across. Or it might be large, hundreds of meters, kilometers. It is dark because most asteroids are very dark, and it is tumbling slowly in the emptiness of interplanetary space, following the invisible rails of gravity laid down by the sun and the planets with perfect, unhurried precision. It has been following those rails for millions of years, billions of years perhaps. It formed in the early solar system when the sun was young and the planets were still coming together from swirling clouds of gas and dust. It has been witness, in its way, to the entire history of our world, the cooling of the earth, the formation of the oceans, the first stirring of life in the ancient seas, the long silent aeons of microbial existence, the explosion of multicellular life, the age of fish, the age of amphibians, the age of reptiles, the long dynasty of the dinosaurs, the catastrophe that ended them, the rise of mammals, the appearance of the great apes, and finally, in the last handful of seconds, cosmologically speaking, the emergence of a species that knows how to look up at the sky and measure the distances between stars. And it has never once altered its course in response to any of this. The first photosynthetic bacterium did not make it swerve. The first fish to crawl onto land did not give it pause. The meteor that killed the dinosaurs had no effect whatsoever on its orbit. And us. Our cities, our satellites, our telescopes, our nuclear weapons, our spacecraft, our philosophies and religions and political systems and agricultural revolutions, to this rock, tumbling through the dark in its ancient orbit, all of it is invisible. We do not exist. Until the day that we might. The universe is very large and very old. It has no center, no edge, no purpose, no preference. Stars explode and die. Galaxies collide. Black holes consume everything that falls within their reach. And in the thin shell of air and water and rock that surrounds a medium-sized planet orbiting an ordinary star in the outer arm of a spiral galaxy, a species of clever primate has built something extraordinary. A civilization, a body of knowledge, a collection of art and music and literature and mathematics and love. All of it is here. All of it is on this one planet. There is no backup. There is no second copy of the music of Beethoven, or the paintings of Rembrandt, or the theorems of Euler stored safely somewhere else. There is no redundant version of the Great Barrier Reef, or the Amazon rainforest, or the Serengeti. There is no second Earth waiting to receive us if this one becomes uninhabitable. The asteroid does not know any of this. It does not need to. We are the ones who know. We are the ones who understand, for the first time in the history of this planet, that the threat is real, that the physics is non-negotiable, and that the window of opportunity to do something about it is neither infinite nor guaranteed. We are the ones who have to choose, and perhaps that is the most extraordinary thing about this moment in history. Not that the threat exists. It has always existed, but that for the first time, the threat is known. And knowing, we have a choice. We can look up at the night sky and see the smudge of light moving slowly among the stars, moving slowly, inevitably, toward us, and decide that the odds are low enough, the time scale long enough, the problem distant enough that someone else can deal with it, that future generations can deal with it. Or we can look up and decide that being the first species in Earth's history capable of preventing its own extinction by asteroid impact is worth taking seriously. That the field in summer, the birds in the trees, the river over smooth stones, the 4 billion years of evolutionary history that produced all of this, all of it is worth protecting. The asteroid does not care either way, but we do. And that, perhaps, is the only thing that matters. The Earth has survived mass extinctions before. Life has always found a way to continue, to rebuild, to evolve into something new. But there is no guarantee that we are part of what continues. There is no law of the universe that says the species that first understood its own potential extinction will also be the species that prevents it. That depends on us, on the choices we make, on the attention we pay, on the resources we allocate to watching the sky and building the tools that could, if we are wise enough and lucky enough and timely enough, move the rock aside. The night sky is beautiful. The stars are beautiful, and somewhere among them, following its ancient, unchanging path, is a rock that does not know we exist. Look up, know the danger, and choose to act. I hope you enjoyed this video. If you did, a like and subscribe would really help the channel. I'll see you next time.